creep. In another word, we can call this as high temperature deformation. I can say this creep mechanism happens in the material when it is exposed to very high temperature under constant loading condition, and it will be keep on deforming as a function of time. Such kind of failures we can call as creep failure. Okay, see here it is described in a clear manner. Creep is defined as the permanent deformation of a material under load as a function of time, and it is appreciable only at temperature above 0.4 melting temperature. Okay, it's a very high temperature range, right? Okay, for your information, I can give some examples. Okay, turbine rotors in a jet engines, steam generators, steam turbine, and boilers are undergoing these creep failures. Okay, actually, these all the objects are operated under very high temperature. So, this failure will be prominent in such stuff. Okay, and while designing such objects or such components, you have to keep one thing in your mind. That means when we are designing, we have to choose special temperature resistance materials like super alloys in order to avoid creep. Okay, creep curve. Actually, it shows at constant loading condition the behavior of creep metal. Okay, and it is drawn between strain and time. That means strain versus time. Okay, initially when conducting the experiment, they used to apply the load. So what happens at that time? The metal experienced instantaneous deformation. Mostly, it will be elastic, and we can see from the graph it is obtaining at the initial this much of strain energy. Okay, and if you look into this diagram, you can see the trace of curve as this manner. Am I right? And if you look into this curve, you can see three regions. Okay, three separation of regions like this. Okay, one is a primary creep, that is taken as the first one, and second the middle layer they are representing as a secondary creep. Okay, and the last one is a tertiary creep, right? And let me concentrate first of all on the primary creep. Just look at this primary creep region. I can say initially the strain rate is increasing. Okay, and as a function of time, it is keep on decreasing. Am I right? The rate is keep on decreasing. From this curve, we can see evidently. Okay, I can say thus the metal experiencing increase in creep resistance because of slowdown in the strain with respect to time. It is been identified that the metal is experiencing increasing creep resistance. So in the primary creep, the metal is resistant to creep, we can say. Okay, and next and the second one is a secondary creep. Okay, look at this region. I can say here you can see the very linear curve. Am I right? Yes, and as well the strain rate is very constant with respect to time. Okay, here this increment is very constant with respect to time, and when we compare with the other creep region, primary creep region and the ternary creep region, I can say here is the long duration. Okay, here is the long duration. Because of this, what happening, it experiencing the deformation. Okay, this in this region, in the secondary creep region, the metal is experiencing the deformation. Okay, and we move to the last one, tertiary creep. And if you look at this graph, I can say here you can see the accelerated strain rate. Am I right? Accelerated strain rate. The strain rate increase with very high manner. Okay, and it ends with fracture. Okay, and this failure is happening in the material. From the microscopic level observation, it is found that because of grain boundary separation, internal cracks, voids, and cavities. Creep is happening in the material because of three mechanisms. First one is a dislocation climb, and second one is a vacancy diffusion, and third one is a grain boundary sliding. First of all, let me discuss this dislocation climb. Okay, and here I have shown you the crystallographic arrangement of metal. These are the things are atoms. Okay, the color variations are nicely provided in order to quite differentiate the things. Okay, here you can see the rectangular box in order to show you the free space, that means vacancy position for the atom. Okay, so in general we know the creep always occurs when it is exposed to high temperature. Am I right? When the metal is exposed to very high temperature, this creep occurs. So here this crystallographic arrangement of these atoms are at very high temperature and it is being stressed. So what happens internally at microscopic level, these atoms will dislocate. Okay, and because of this dislocation, the dislocation motion cause this atom to diffuse into the what vacant position. Okay, because of this dislocation motion, what happening, this atom is diffused into the vacancy position, right? Here you can see it is described nicely. At high temperature, atomic movement permits dislocation to climb. Okay, and because of this, what is happening, this atom is climbing a next region, right? Because of this dislocation climb, the diffusion rate of the vacancy may produce a motion in response to applied stress. Okay, this motion will be in response to the stress applied to the material. Okay, and let me move to the next mechanism, that is vacancy diffusion. In favor of understanding this vacancy diffusion, I have shown you the grains and grain boundaries. And first of all, I have applied the stress here. Okay, at both the end I have applied the pull, and you can see both the end of the boundaries, it is filled with the atoms, and these atoms are arranged just parallel with this applied stress. Okay, and now just consider the applied stress is acting over this grain for a period of time. Okay, what happens, the specimen obviously it will be get elongated and it will be contrasted in transverse direction, right? It will be going on just like this manner. So as a result, I can say these atoms will be just get migrated to the boundary just perpendicular to the applied stress, and it will be forming as this manner. You can see from the B diagram. Okay, you can see from this diagram, and as a result, what happens, the creep will be causing in the metal. Okay, this is a final diagram. Actually, this is the final diagram, and if you look into this final diagram, you can see the direction of flow is mentioned as this manner. You'll think actually the atom is taking off the motion as this manner. Am I right? This is taking the movement as this manner, but the direction is shown here as this manner. This is because of here it is shown as this manner in order to represent the vacancy migration. Okay, in order to represent the vacancy migration, this vacancy migration will be noted in the diagram just opposite to the atomic migration. Okay, so such a manner it is provided in the diagram. It is the lost creep mechanism. Here I have shown you the grains and grain boundaries. These are the grains, these are the grains, and these are the grain boundaries. Okay, these are the grain boundaries. If the metal is exposed to very high temperature, if the metal is exposed to very high temperature, the grain boundaries will be, this grain boundaries will be very weaker when compared to the grains. Okay, the grain boundaries will be very weaker when compared to the grains. Because of this, the grains will slide with respect to one another. This will be getting slide with respect to one another, and this will cause the creep in the material, right? So here the note is given. At low temperature, it provides effective obstacles to dislocation motion. At high temperature, the grain boundaries facilitate the deformation process by sliding. Okay, so by this we can end up the session. Thank you.